Here, I'm going to dot the v and u, right? So we already did that right there. That was -3, 7, dotted with 2, 4. And then the only difference on the bottom is that when we do this magnitude down here, we're not going to square it this time, are we? And so when we did that dot product on the top, was it 22?
Yes.
22. And then over, this time we're not squaring it, so it's not 58, it's what? Square root of 58, right? Because we never square it? That's it. Questions? Yes?
Could you treat the magnitude of v squared as v dot v? Would it be more useful or not?
You could. Yep. So the question is, and that's good, I'm glad you made that connection. Earlier in this particular section, I actually showed you this property that if you take u and dot it with itself, it's the same as the magnitude of u squared. So the question was, could you, in this formula right here, replace that with v dot v? And the answer is yes, which almost leads back to your question a minute ago. If we change that to v dot u, and we replace that bottom with v dot v, can you cancel the v's, right? You can't. You got to do this operation first, and then you can do it. Because these are vectors. The dot product gives you a number, so just it's.
Right, I was just assuming because since the magnitude is a scalar value. Right?
Yeah.
Right, I assumed from like associative property that you could like take it outside.
Gotcha.
No, the vectors work in different, have different, I keep on saying, order operations.
The operation in the numerator on yours was a dot. That was the only issue.
I would also throw out that if you did cancel that out, you'd be left with u times v. And I don't know how to do that operation. U times v.
Yeah.
Yeah, because
we don't know because that's a scalar multiplication. You can't take two vectors and scalar multiply them. You can only dot product them. All right, we're going to continue.
Additional set of problems.
So we got this projection idea down, I hope.
Seems all right.
All right, this next one here is weird. So I give you this vector that lives in R2, R3, what? That vector lives in R3, right? So we're in three-dimensional space. We got this, yes?
I had a question.
Yeah. Oh, I'm sorry. You should have just stopped me.
You look like you have fun.
Okay.
Just so I have my terminology correct, it's for the comp. It's comp v on u or comp u on v right there.
Well, it depends on what I want you to do.
Right there. How would you read that?
This would be the component of u onto v.
Okay, that's what I was trying to ask.
Yes, that's the way you'd read that. The component of u onto v. So whatever's in the subscript is the thing you're projecting onto.
Okay,
That's the way I look at it. Yes?
Because y is 0, isn't that just an xz plane?
You could look at it as the xz plane. The only issue with that is that in this problem, you actually could get answers that are not just in the xz plane. You could get solutions to this that would live outside. So we don't want to convert it to a two-dimensional problem because it's actually got solutions in three-dimensional space. So let's understand what the question is asking first. We've got this vector living in three-dimensional space, right? Let's say from here on out, when I hold a vector in my hand like this is the tail right here, right? That's tip. Okay, so I've got this vector in space, right? And what I'm trying to do is find some other vectors, right? Find a vector v. Here it is. Let's fix this one. Find some vector v out here so that when I take the component of u onto v, so that when I project the shadow of this vector onto this vector, it has the shadow of this down onto this has a length of 3.
Oh.
Right? That's what this says. The component of u onto v is the length of that projection vector. And I want to know when that length is 3. So should we only have one answer? Like let's just say I hold this in the right way, that if you drop straight down from here to here, that length is 3.
Shouldn't there there be almost an infinite amount of vectors, just the same direction is what matters?
So, well, would it be in the same direction? Do y'all see, does anyone see the shape of all, if I put all the vectors that are an answer to this, if I were to put them all and like draw them all, do you know what it would look like? A cone. Good. Who said that? I just heard it. It would be a cone. It would be the cone that goes around like this. Comes around like this. Because if you take any vector like that, the projection down is 3, right? Bring it over here, projection down is 3, projection down is 3, so you would get this cone, wouldn't you?
So it's pi coming to place?
No. This is just for us to visualize that there's more than one answer, right? There's an infinite number of answers, but they're not arbitrary. They all live on this like cone-shaped thing, right?
Isn't the length of V also, like, isn't the length of V effectively arbitrary?
Yeah,
Because it's the angle that matters, but the length, it could be,
yeah.
okay.
Yeah. All right, so let me just go after this, all right? I want the component of u onto v to be equal to 3. So I'm going to start by writing down what the definition of component of u onto v is. The component of u onto v, need that to be equal to 3. So we need this, right? We need, or we want, you can say want, the component of u onto v to be equal to 3. By definition, the left side is v dotted with u over magnitude of u, v. What is it?
V.
What is it?
Magnitude of V.
V, magnitude of v. Okay,
It's always a small one.
what's that?
It's always a small one in the notation, right?
It's always the one that you're projecting onto, which it doesn't have to be the smaller vector because it could be longer, right? So
It's always the subscript.
it's always the one that's subscripted, yep. Okay, we need that, right? We need that to be equal to 3, don't we? All right, so let's see if we can figure out what this is over here. I need to take the v vector and dot it with u, right? Now, I know the u vector, right? It's given to me, but I don't know the v vector. Nobody gave me the v vector. So I'm going to write the v vector as an arbitrary vector. So I'm going to write v over here to be equal to v1, comma v2, comma v3. In other words, v is some three-dimensional vector that has 3 components, v1, v2, v3. I don't know what they are, right? I don't know what v1, v2, and v3 are. And then, of course, u is that 4, 0, negative 1. So this is like scratch work over here. Let me dot these. If I take v and I dot it with u, that's the same as taking, three-dimensional space gets in my way sometimes here. Let me do that. All right, so if I take v, that's v1, v2, v3, and I dot it with u, which was 4, 0, negative 1, I can do that mechanically, right? Like mechanically, I know what to do here. Multiply the first components, add the multiplication of the second, add the multiplication of the third component. So what would I get there? 4v1. V2 kills off, doesn't it? 0 times v2, gone. And then you have negative 1 times v3. Right? That's a dot product.
Yeah.
Okay, let's continue. No, I did the dot product, so the 0 times v2 was dead, right? Now, I need the magnitude of v. Well, I don't know what the magnitude of v is, right? Yeah. I just know what it is in terms of a formula. It's the square root of whatever the first component is squared, plus whatever the second component is squared, plus whatever the third component is squared, right? That's the magnitude of v. So all this is just me kind of setting up the things I know, and now I'm going to come back over here and start plugging things in. So v dot u was 4 v1 minus v3, and then over the magnitude of v, which was the square root of v1 squared plus v2 squared plus v3 squared. That has to be 3, right?
Yeah.
There you go. We just need to figure out what makes that 3. We have a little bit of a problem, though. we have one equation, and we have three unknown variables, right? And it's not linear, so linear algebra is not going to help us because this is not a system of linear equations. This is non-linear equations, so it's a totally different thing. So we need to figure out if we can solve this. Well, here's the thing: we cannot find a unique, like we will not be able to find a solution, a single solution. There will be an infinite number of them. Like we said, the cone, right, that goes around. So in the instructions, I just said find V, right? I just said find V. I should have put in there find any V, but I didn't want to give away the fact that there's an infinite number of solutions. So I'm going to go back now and kind of edit my question. I want us to find any V that will satisfy this equation. Yes?
Is this like a domain question? Like find a v that's greater than this that will satisfy where it's greater than 3?
Well, we do have some restrictions on V1, V2, V3. We do have some restrictions, like if you want to, you consider that to be some sort of domain restriction. Like right now, could we let the V vector be the 0 vector? Why not? What would this be? 0, division by 0, not going to happen, right? So not any V works, right? Not any V. They all have to have certain like qualities to them. Relationships have to be in place. Yes.
So, trying to think, so couldn't you, like, graphically describe something like a plane through a sphere?
A what?
A plane through a sphere?
A plane through a
So
sphere.
the denominator, numerator describes, like, if you have the set the top equal to 3, like 3 over 1 is equal to that's on the left. So couldn't you make like a linear equation from the top, and then the bottom describes a sphere, right? This is it V1, V2. If you were to plot all those points in space.
Yes. That's right. But I can't expand on that much more because we as a class haven't really talked about the fact that this is the equation of a plane and that's the equation of a sphere, and therefore we're going to get there. We're just not there yet, right? So yes and wait. It would just be too much for me to say, yeah, let's keep going with that. You know? But be careful, because what you're saying is that the solutions to this, the V1, V2, V3, the solutions are the intersection of a plane and a sphere, so to speak. But has nothing to do with the vectors. Once you find those solutions, then you create vectors from them. So I just want to be clear. They're not exactly, okay. All right, so let me continue here. What I'm going to do next is I'm going to just try and clean this equation up a little bit by just taking the square root to the other side by multiplying both sides by the square root. That's fair, right? That's legal algebra there. And then I'm going to go ahead and do something we love doing with square roots. To get rid of them, square both sides of the equation. So when I square the left, I'm going to have to expand this, right? I can't just square each term. I can square the 3, and then when I square the square root, it goes away. And now I'm just going to leave it like this for right now. I'm going to try and see if I can find a V1, V2, and V3 that make this true, all right? But like I said before, we have 3 unknowns and we only have 1 equation. So whenever you have that situation, the best rule of thumb to get a particular solution is just to let one of the variables be anything you want it to be, and just see what happens, all right? So let me try something. At this point right here, I'm going to box this. This is kind of like my master relationship here, all right? And that is, let's let V1 be 0, all right? I'm just going to try to see what happens if I imagine that the first component of my vector V is 0. All right, so if V1 is 0, what is the left-hand side what does the left-hand side turn into over here?
V3 squared.
Just negative V3 squared, right? And when you square the negative, it becomes positive. So you get V3 squared on the left. What about on the right? If V1 is 0, you just have these two, right? Okay, so that would become a 9 in front of, I'm going to distribute the 9 through to both of those. Okay, so the V1 went away, and then I distributed 9 through to both of those. So if I imagine letting V1 be nothing, 0, then this is the new relationship I would have between V2 and V3, right? And now let me get all my V3s on one side. So let me move this to the other side. What does it become over there? Negative 8. V3 squared must equal 9 V2 squared. And at that point, I say, shit, that doesn't work. Why? Why is that going to work?
The negative makes it impossible because
That's right.
the variables
Both of these are, no matter what you choose now for V2 and V3, no matter what you choose, they're going to both be squared, aren't they? And so that's going to be a positive number. And so you have a negative number times positive must equal a negative times a positive. So a negative has to be a positive. Not happening, right? Unless you let them be 0, right? But if you let those both be 0, then we have the 0 vector. And the 0 vector doesn't work. So this doesn't work, which means I can tell you right now that the V's we're trying to find, this cone, right? This cone of V's, none of them have a first component of 0. None of them. All right? So since that didn't work, I'm going to try something else.
Let V2 equal 0.
We could let V2 equal 0. We could let V3 equal 0. We could let V1 be 2. It's totally up to us. I like to pick things that are nice, like 0, because it's always a good starting point. Yes?
Theoretical question. Wouldn't a good place to start be to pick one that was in our original vector so that we would know it was at least in a line with it, like on the same plane? Like, wouldn't that be actually a pretty solid way to start?
I think if you ever have an equation, a single equation with 3 unknowns, I think letting one of the variables be 0 is always the best way to go because it clears it out of the equation.
Okay.
Yes?
Can we just also draw, say, the u vector, and draw, and we know the composition is 3.
Mm-hmm.
So therefore, we theoretically know an x and y component, and we can just use that.
You could try drawings,
use that,
yeah.
what do you call it? X, or the first component of the composition vector to
Component.
as our plug-in for P1, per se, because,
Yeah.
because it's a cone that has to be fixed. You have a cone.
My first problem with that is just, I mean, may work, but my first issue would be, okay, are we going to start drawing vectors now in 3-dimensional space and feel comfortable with finding another vector?
You don't need to draw it.
I thought you said we could draw it.
You can just draw it right.
Okay.
It's representative of the cone, but on a 2D surface, because you have
Can we, do you have time after class? Okay, because I want to see you like kind of show me.
It's a lot easier if I draw it out.
Yeah, let's do that after if you have a few minutes.
Okay.
I'm going to let V3 now be 0. Now I chose V3 for a reason, to be 0, not V2. And that's because V3 appears right here, and that will go away. And then V3 here will go away. So it's just, if I let V2 be 0, then it's only going to kill that one. It's just more work for me. You see? So I'm just going to let V3 be 0, and then I'm going to rewrite this equation. It becomes 4V1, that has to be squared. And on the other side, my V3 is going away, so I'm going to have 9V1 squared, plus I'm distributing. That's right. I hear that alarm a lot. My dad, that's iPhone stuff, right?
Yeah.
So my dad had bladder cancer, and so he had to have a surgery where he has a little bag. And so that goes off every 15 minutes, 20 minutes that I'm with him. Every 15, 20 minutes he has to go and just check.
That's my warning alarm.
Yeah.
Every time I hear it, no matter where it is, I get a shot of adrenaline.
Yeah? So that just woke you up. You ready to go? Let's do it. Not in here, though. When you hear it in here, it puts you to sleep. All right, so here we're going to square this, right? So we get 16 v1 squared. And then this, right? And now, look, if I move my v1s to one side now, how many v1s will I have here? 7 v1 squared equals 9 v2 squared. And hey, this will work. This time it'll work because this is not ever going to give me like negative equals positive. So now what I can do is just let's solve for v1. v1 squared will be equal to 9 over 7 v2 squared, right? Take the square root on both sides. I'm almost done. v1 will be equal to the square root, and I need to do plus or minus because there's actually two possibilities here, of 9 over 7 v2 squared. All right, so I need to pick a v2 now. What would y'all like me to pick for v2? Remember, I've already picked a v1. Oh, wait, no, the v1 didn't work. Right now, I have a vector v, and all I know about that vector v is that the v3 is 0. I still need to figure out v1 and v2. So
0 for v2.
if you do 0 for v2, then what's v1? 0. Doesn't that seem like a nice choice?
Yeah.
Wait a minute, didn't we say that v1 couldn't be 0?
Yeah. So we can't do
So, yeah, so if we pick 0, they're both 0, and they're all 0, so we can't do it, right? Okay, so you can't, so what did I hear? I heard 1, so if you do 1, that's nice because you don't have to worry about it, but then you have to take the square root of something that's not nice. I heard also, hold on. I also heard, I thought I heard 7, right? I also heard 7. What's good about 7? What's 7 squared? 49 divided by 7 would be 7. I don't want 7 in there. Square root of 7? How about square root of 7? If I put the square root of 7 right there, then you square it, you get 7, then the 7's canceled, then you take square root of 9, you get 3. So I'm just, look, you could pick any number you want, all right? Any number you want. You want to go with 1, go with 1. I'm going to pick something that I know I'm going to get a decent number when I get done with this. So now, at this point, I let v2 be equal to the square root of 7. And if I do that, do I have to do the work? Can everyone see square root of 7 squared is 7, 7's canceled, then you have a 9, root 9, you get plus or minus 3?
Yeah.
So this will be plus or minus 3 for my v1, and this was the square root of 7, wasn't it? That is one particular answer. That is one particular answer, yes.
For one particular answer, shouldn't we choose a plus or a minus then? Because
Oh, sorry, I should say 2 particular answers. Sorry, yes. I should say that is 2 particular answers because I put a plus or minus, right? All right, I would like to check my answer, okay? Because I did a lot of stuff there, I just want to make sure it's right. So how could I check it? I actually could take the component of u onto v and make sure it's 3, right? So let's actually do the component of u onto v right now, because I know what v is. This is v dot u over the magnitude of v. So now what I'm doing is I'm dotting the v vector. Let's take just the positive 3 here. 3 root 7, 0. I'm going to dot that with the u vector, which is 4, 0, negative 1. And I'm going to divide that by the magnitude of this vector. So I need the magnitude of this vector right here, right? So square root of 9 plus 7. Okay, what do we get when we dot up top? There to there? 12. 12. That's all we get, right? Everything else goes away?
yeah.
And then over here, that's square root of 16, which is 4, and that is 3. So That just checks that it did work. All right? Okay.
Nice if they all came up to such a nice little number.
Yeah, I did this problem the other day just to make sure. I haven't taught this class in like 3 years, so it's been a while since I've gone through all this. 2 or 3 years. Seems like 10. And so I just went through a problem, and I picked a different V and so I had a little uglier stuff here, but it all comes out to be 3 if you do it right. All right, we are done with this section. All right? We are done with this section. We are ready to move into the next section. If I can see my cursor, there it is.
So wouldn't the negative when you come out negative on top, so that would be or would it matter? Well, when you
On the-
do V,
On the,
because when you dot U and V, doesn't that come out to negative 12 over 4? So that would be,
yes, so
that
you,
wouldn't ask the question then, right? Because it's supposed to be V equals 3. Well, I mean,
it's a length. It'll be negative, right? So when you talk about component, you're talking about the length of that vector, right? So when you're finding that, you're finding the vector. Let me think about this for a second. 3 negative. Hold on a second.
What is that? He's asking
well, I guess
if
the
you came
component
out
would
with
be
all-
The negative.
If you use the negative, it would get to the
On the because the bottom would still be what?
the projection is back.
Bottom's still 4, right? But your top would now be
negative.
negative, right? So I think we're going to, you know what, you're bringing up a good point. I think we're going to have to check our answers. Because we took a square root, right? So there's a possibility of extraneous solutions and stuff. Or we square, sorry, I should say, we square both sides. Anytime you square both sides of an equation, right, you always introduce the possibility of extraneous solutions. So if we had plugged in the negative 3, then we would have seen that it didn't work and we would throw it out. Because that gives you negative 3, not positive 3. Yeah. Remember, our goal is to try and find like one answer, right? So I found what I thought would be 2 answers, right? I used the positive 3, it works. If you use the negative 3, it doesn't. I'm glad you brought that up. All right, we're moving on to the final type of multiplication between 2 vectors, and that's the cross product. All right, so when you take 2 vectors, right, you take 2 vectors and you dot them, you get what? You get a what? When you dot 2 vectors? You get a number, a scalar, right? And that number somehow indicates gives you some idea about the angle between the 2 vectors. If the dot product is positive, it's acute, negative, obtuse, and if the dot product is 0, you have orthogonal vectors. The cross product, you take 2 vectors, you do their cross product, and the result is not a number, but a new vector. You get a new vector out, all right? And the first thing we're going to do is we are going to see how you actually do the dot product mechanically. And then we'll talk about what it gives you. Like we know, I'm telling you it's a new vector. We'll talk about what the properties of that vector is. But first, let's make sure we can do a cross product, all right? Because dot products were pretty straightforward, weren't they?
Yeah.
They're pretty straightforward. Cross products are not as simple. The formula is not as easy. This is the formula, and this is the notation. If you have 2 vectors, show of hands, how many, I know a lot of you have done cross products, yes? Physics somewhere? No? Never done a cross product? Okay. So if you've never done it, pay attention. If you got 2 vectors, u and v, these are 3-dimensional vectors. So there's a little caveat, a little catch here that I kind of slipped by you. And that is cross products can only be done in 3-dimensional space. All right? You have to have a 3-dimensional vector and a 3-dimensional vector. Now, there's a workaround. If you're in 2-dimensional space, you can always extend out to 3-dimensional space. I will do it later this semester, so you don't have to worry about it. So even though I'm saying you need 3-dimensional vectors, in 2D we're going to be okay. All right? So just stand by on that. For now, here's the definition. Take a vector u, 3 components, u1, u2, u3. Take a vector v, v1, v2, v3. This is the angle bracket notation. This is the I hat, J hat, K hat notation that we kind of talked about a little bit last class. Doesn't matter, you have a vector, right? And here's the formula for U cross V. Nasty, right? Nasty. Go, if you want to memorize it, go for it. I don't care. I have a better way. There's going to be a better way, all right? But that's the actual formula for it. Let's see what it's telling you to do. Take U2, multiply by V3, then subtract U3 times V2, and that right there is going to be your I hat component. So this is like in an angled bracket notation. This right here goes in the first component. This right here is your second component, and then this right here is your third component, and your answer, that's your answer as a vector. Nobody likes to memorize this formula, all right? Because it's a lot to have to figure out, right? Keep things in order, yes? Also, if you do the cross product the other way, backwards, you don't get the same result. So remember, dot product was commutative. The cross product is not. All right, now I will address that a little bit in just a second. So let me show you the easier way to do it. Or not, I'd say easier. There's like 3 or 4 ways that are taught on how to do cross products. So the way that I am going to show you, I think is the easiest. All right? But to do it, I need to make sure you understand what a determinant is of a matrix.
Oh.
All right? So you may or may not have seen this ever before. So we're pausing right now on cross product. Just for a moment, we're pausing. And we're going to talk about a determinant of a 2 by 2 matrix. And this is not, when I talk about determinant right now, we're not here to get into the theory of what a determinant is, what it's used for, blah, 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 because that's a whole other conversation. This is really just mechanically, how do you find the determinant of a 2 by 2 matrix? Because the mechanics of it is what we need to do a cross product. So if I start with a 2 by 2 matrix, all a matrix is just a list of numbers. So you have a number, 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 and then you put a bracket here, bracket there. That's a matrix, all right? The determinant of that matrix, the determinant, we usually denote it this way, determinant of that matrix A, B, C, D is A times D minus B times C. All it is this number A times that number, A times D, and then you subtract from that these two numbers multiplied right here, B times C. That will give you a number, and that is the determinant of the matrix, and it's used for finding inverses and things like that, and blah, blah, blah. Kramer's rule, whatever. If you've seen it, you've seen it. If you haven't, don't worry about it. Oh, I forgot a parenthesis over here, all right? So that's the definition of determinant. Any questions? Just a mechanical process. You just have to remember this and this. Subtract, take that,